Good morning. Let's see the next point of unit number 4. When a fluid is flowing over a stationary body, a force is exerted by fluid on the body. Similarly, when a body is moving in stationary fluid, a force is exerted by the fluid on the body. Also, when the fluid and body both are moving at different velocities, a force is exerted by fluid on the body. Some examples we can say: flow of air over the building, flow of water over the bridge, ships, aeroplanes and automobiles having through water or in air. In this unit, we are going to see the force exerted by submerged bodies. So here in this example, one aeroplane is shown. When aeroplane floats, lift is responsible for its upper moment, which is working against the gravity, and drag is responsible for working against the thrust. So that concept we are going to see. Here we are considering a body. This is body which is held stationary in a real fluid. There is a real fluid which is flowing with constant velocity capital U. The fluid exerts the force on the stationary body, and that force exerted is Fr. That is the total force on the body, and that total force is perpendicular to the surface of the body. Thus, the total force is inclined to the direction of motion. This is inclined to the direction of motion. The total force can be resolved into two components. One is in the direction of motion and other in the direction perpendicular to the motion. The component of total force in the direction of motion is called as a drag. This component is denoted by Fd. Thus, the drag is the force exerted by fluid in the direction of motion. The component of total force in the direction perpendicular to the direction of motion means this force is called as a lift. This is denoted by Fl. Thus, the lift is the force exerted by the fluid in the direction perpendicular to the direction of motion. The lift force occurs only when the axis of the body is inclined to the direction of the flow. If axis of the body is parallel to the direction of flow, lift force is 0. Remember this word. If the axis of body is parallel in the direction of fluid flow, lift force is 0. In that case, only drag force acts. If suppose fluid is assumed idle and body is symmetrical as a sphere or cylinder, both drag and lift force are 0. Now we will see the expression for drag and lift. In this figure, we have one solid body which is having arbitrary shape. It is also placed in the real fluid which is flowing with uniform velocity capital U in horizontal direction. Consider small elemental area. Here we are considering small elemental area which has value of dA. Then force acting on this area. Then the different forces acting on this area, we can say here, concentrate on this. This is the area dA. We have to calculate the different forces acting on this. First is the pressure force, that is P into dA. P is the pressure, dA is the area, that is pressure force. Then there is another force which is nothing but shear force, which is in this direction, and it has value shear stress tau 0 multiplied by area. Let the angle made by the pressure force is theta with the horizontal direction. The drag force we can calculate the drag force on elementary area, force due to pressure in the direction of motion plus force due to shear stress in the direction of motion. Consider this diagram. In this diagram, PdA is the pressure force, and this pressure force have two components. One is in the direction of motion, another is in the direction perpendicular to the motion. Similarly, the shear stress tau dA has also two components. One is tau dA cos theta, another is tau dA sin theta. Drag force Fd is equal to force due to pressure in the direction of motion plus force due to shear stress in the direction of motion. So how we can calculate mathematically? PdA cos theta plus tau 0 dA cos 90 minus theta, which is nothing but this tau dA sin theta. So we can rewrite P dA cos theta plus tau 0 dA sin, and total FD we can calculate by taking the integration. Here dA with respect to dA we have to take the integration. So we can rewrite the equation: integration P cos theta dA plus integration tau 0 sin theta dA. So here is the first equation for drag force. The term P cos theta dA is called as a pressure drag or form drag. Integration P cos theta dA is pressure drag or form drag, while the tau integration sin theta dA is called as a friction drag or skin drag or shear drag. Skin drag or shear drag. Remember these names: friction drag, skin drag or shear drag, and pressure drag or form drag. Let's move to the next point. Okay, next point is a lift force. First, the lift force is nothing but force due to pressure in the direction perpendicular to the direction of motion plus force due to shear stress in the direction perpendicular to the direction of motion. So we can write the equation FL, that is lift force, minus P dA sin theta. Why minus sign? Because it is in the opposite direction. This, it will be minus, plus tau 0 dA cos theta. The total lift will be integration tau 0 dA cos theta minus integration P dA sin theta, which we can rewrite integration tau 0 cos theta dA minus integration P sin theta dA. This is second equation. The drag and lift for the body moving in a fluid of density rho at uniform velocity u are calculated by next formula, that is Fd is equal to CD into area into rho u square upon 2, and FL is equal to CL into area rho u square upon 2. CD and CL are the coefficients of lift. This is coefficient of lift and this is coefficient of drag. CD and CL are the coefficient of drag and coefficient of lift. And A is the area of the body, which is the projected area of body perpendicular to the direction of flow. Then resultant force Fr is nothing but under root Fd square plus Fl square. So this is all about expressions of drag and lift. Everything I have given here in this slide you can refer. This is drag force, this is lift force. Coefficient of drag, coefficient of lift. Free stream velocity, density of fluid. It is a simple alternative of the lift and drag force. This and this. Moving to the next point. Here you can see screen friction drag and pressure drag. One body is there which is kept in the direction parallel to the motion. Only shear force will act and the boundary layer is formed. And pressure drag, here body is kept in the direction perpendicular, so here wakes are created, low pressure zone is formed. Drag force depends on the shape of the immersed body, position of the body immersed in the fluid characteristics and flow characteristics. There is one concept, bluff and streamline bodies. Bluff body is defined as the body whose surface does not coincide with the streamline. When flow is separated, here flow is separated from the surface of the body much ahead of its trailing edge, with the result of very large wake formation. Here large wakes are formed. Then the drag due to the pressure will be very high as compared to the drag due to friction of the body. Thus the bodies of such shape in which pressure drag is very large as compared to the friction drag is called as a bluff body. Opposite to that, defined as the body whose surface coincide with the streamlines. When the body is placed in a flow, in that case the separation of flow will take place only in the trailing edge. Here boundary layer will starts at the leading edge. Boundary layer will starts at the leading edge. Here is the leading edge. Will become turbulent from lamina. Yet it does not separate up to the rearmost part of the body in the case of streamline body. Thus, behind the streamline body, wake formation zone is very small. Here, wake is formed, but it is very small. And consequently, pressure drag will be also small. Then the total drag on the streamline body will be due to friction only. That is nothing but due to shear. The body may be streamlined at the low velocities but may not be at higher velocities. When placed in a particular position in the flow but may not be so when placed in another position. So here is the example. First is a bluff body, last is a streamline body, and sphere where both the drags are present. Pressure drag is also present. Friction drag is also present, pressure drag is also present. In bluff body only pressure drag will be there. In streamline body mainly friction drag will be there. Just remember this concept. Here is another way of showing the bluff bodies and streamline body. Here large amount of wakes are formed. Boundary layer is there. Here is the separation point. Due to that boundary layer separation, large amount of wakes are formed. Here is second is the streamline body where the separation occurs near to the ending edge of a body, and pressure drag is minimum, and here pressure drag is maximum. So blub bodies are not recommended. Drag coefficients of different bodies: for sphere it is 0.47, for half sphere it is 0.42, cube it is 1.05, streamline body it is less, and streamline half bodies it is also less as compared to the other, that is drag coefficient. Let's have a look about flow around a circular cylinder. Laminar flow around a circular cylinder is shown here. Here in the second diagram you can see turbulent flow over the cylinder. Here are some considerations for both: how the positive pressure is created here and how the negative pressure is created on the other side. There is one concept, development of lift on a cylinder due to circulation, which is nothing but Magnus effect. When a cylinder is rotated, this is cylinder, this is the cylinder, it is rotated in a uniform flow. The lift force is produced on the cylinder. This phenomena of lift force produced by rotating cylinder in the uniform flow is known as a Magnus effect. It is a simple concept. There is a uniform flow. Inside that uniform flow we are having cylinder. It's the top view of a cylinder, and when it is rotated in that flow, then there is a formation of lift force due to rotation of the cylinder. It is called as a Magnus effect. Then next point is consider a aerofoil and flow around it. When we consider a aerofoil, then there are some concepts. When we consider aerofoil, which are streamline bodies which may be symmetrical or asymmetrical. Aerofoil shown here is unsymmetrical. It is characteristic by its chord length and angle of attack alpha, which is the angle between direction of flow and the chord line, and the span L of the aerofoil. The drag force on the aerofoil is always small due to the design and shape of the body, which is streamline. Here is the explanation. This is the chord, this is the angle of attack, this is the platform area. Here drag is created, here lift is created, and this is span. It will be also shown by L later. This is symmetrical aerofoil. So here is the example, lift on a aerofoil. When there is a slow air and there is a fast air, and there is example of fast air above and slow air down. So what happens? Pressure exerted by slower moving air and pressure exerted by faster moving air creates the lift. Here you can see, faster the speed, lower the pressure. Here lower in the bottom side, lower the speed, higher is the pressure. So from here pressure will be exerted on the upper side. Like that it will create the lift. So there is one equation which you have to remember. FL is equal to pi c rho u square sin theta into span length b, and CL is 2 pi sin alpha. The pressure distribution on the aerofoil: the upper surface of the aerofoil velocity is greater than the free stream velocity. Pressure is less than free stream velocity. The lower surface of aerofoil velocity is less than free stream velocity, and pressure is less than free stream. So with this we have mostly completed all the parts of the forces on immersed body. The numericals are remain that we will cover in the upcoming lectures. Thank you one and all.